Okay, so here's what we were talking about last time. We were talking about integrals. So, an ultra brief reminder of what we talked about. First of all, I gave you all a quick reminder of, fundamentally what are integrals. And the big idea I want you all to take away from that question is that they're Riemann sums, right? That deep down, fundamentally, by definition, that's what an integral is. And good thing that they are, because there's a tremendous number of applications, lots and lots and lots of applications, which do not in any obvious way relate to area in any way, right? But they're all Riemann sums in the sense that you can take, whatever the problem is. Maybe you're computing, the amount of work that it takes to, push something along a certain distance where the force varies, right? So you can't just say force times distance. Well, the idea is that work is an accumulating quantity. The total amount of work, well, it's the sum of, how much work did it take to do the first couple inches, and then how much work does it take to do the next few inches, etc. You can break up the task into little pieces, look at how much work it takes on each little piece, and add those up. So, by the way, the shortcut term that I'm going to use to describe these kinds of quantities, things that add up over having been chopped up into little pieces, I'm going to call that an accumulating quantity. So work is an accumulating quantity. And if you write down exactly, how would you accumulate all that work, it's a Riemann sum, is the point, right? So we define integrals to be Riemann sums, so that integrals will be relevant to all these huge numbers of applications that we want to be able to deal with. Right? It's not about area under the curve. Most of the time, you don't really honestly need to compute an area under a curve. Okay, right. So with this in mind, get rid of all these little dots. We want to do the same thing now for two-dimensional domains. Okay, what if instead of something accumulating over an interval, what if there's some quantity that accumulates over a region? Right, so lots of different examples that we talked about. We'll get to those in a second. But the big idea is, it's still chop it up, add it up. So each domain, you can slice it into a bunch of little pieces. On each little piece, in that little piece, who knows what your integrand is, but there's some function you're going to multiply by the size of that piece. If you're computing mass, then it's density. If you're computing people, it's population density. If you're computing, a volume under a surface, then it's height. Right? But for whatever reason, depending on the application, some function is going to get multiplied by size, and then you're going to add up over all of the pieces and take a limit to make the round-off errors go away. So we motivate this new expression here. We call it a double integral, and we give it this notation because it's basically just the accumulation strategy adapted to a two-dimensional domain instead of a one-dimensional domain. Okay, we saw some applications. Suppose you want to compute a volume under a graph. Well, on each little piece, on that little piece, right, I'm going to want to multiply the size of the piece. How much area have I got in here? That area, I'm going to want to multiply by height. Namely, the function whose graph I'm looking at. Right? Height times area gives you volume in this case. And this kind of volume accumulates over the area, in the sense that if you chop up the area into little pieces and look at the volumes individually, and you add up all those little slices of volume, you get total volume. Okay. All right. Likewise, for other examples, mass accumulates. Total mass is some of those little pieces of mass, each one of which is density times size. Suppose you're computing a total number of people. Well, look, the number of people sitting in this region is, it's population density times area. And again, people accumulate also. Okay, so that's where we quit last time. And moving on, how do you actually compute these things? So here was our sort of roadmap of how you're going to use Riemann sums. Applications connect to Riemann sums. Saw several examples of that. I think you can probably anticipate, by the way, that there are more applications. I mean, we just saw a couple of quickies, right? But there's loads of them. Okay. So this accumulation strategy is going to be a big deal. The story does not end here. We need to have a technique now to compute these Riemann sums. And just for sort of convenience, we're going to say now, we need a technique for computing double integrals. Remember that shorthand notation there. It's just a shorthand notation. All that means is Riemann sum. Okay. That's how we compute double integrals. I'm going to make a tricky argument. I'm going to seemingly start answering a different question, and then I'm going to pull a fast one at the end. And by the way, this is not intended to be a rigorous argument. A rigorous argument involves some stuff that I don't want to deal with in Math 212. The argument I'm going to give you is it's less rigorous, but it's more intuitively satisfying. And I think that's what's appropriate in a class like this. So I'm going to start off by asking the same question that we just asked a minute ago, but answer it in a different way. Namely, let's compute the volume under some surface. Now, we already know the way you compute the volume under a surface is double integral, right? You can take this region down here and chop it up into little subregions, and you look at the volumes of the little French fries that sit over those subregions, and like that, double integral. But let's do it differently now. And I remind you, you've already computed volumes in Calc 2 classes, right? Volumes of rotation, where you take an area and you rotate around an axis and you get some, kind of vase-looking shape, and you want to compute the volume inside of that rotationally symmetric kind of vase thing. And the big idea was, as you go across, you multiply the cross-sectional area times the thickness of the little slice you're taking. And in this case, since we're going in the y direction, I'm going to call that dy. But I hope you all remember these cross-sectional area arguments from computing volumes of rotation. This is morally equivalent in a way. I mean, of course, the cross-sectional area here is not a disk, right? Like it was when we were doing this in single variable calc class. But it's nevertheless, look, area times thickness gives you volume. I think that's satisfying. Okay. And again, we're dead in the water. In the single variable context, we would say pi r squared and go on, and integral, right? This is not a barnyard variety geometric figure. It's a weird looking shape, and we don't know how to compute the area of it. Wait a minute, or do we? Do we know how to compute the area under this thing? Here's the big idea. That thing, this area that we want to compute here, if you would, work with me on this, that area is the area under that curve. And where have we heard that expression before? Area under a curve. Area under a curve is itself computed with an integral. Right, so I'm going to compute that area with an integral. Now let's think through the details. Integral of what? Well, I need to be adding up these heights. Those heights are the same as these heights. It's the height up to this surface, which is the graph of some function. So z is equal to f of x y, my original surface, and so that height is f of x y. So it's just an integral of f of x y. Now this is a little bit scary thing to look at. Can you do a single variable integral of a function that has two variables in it? We never did that back in Calc 1 classes, Calc 2 classes. Well, I claim this, as I'm writing it down here, only has one variable. Looking specifically at what we're computing this area, right, as it goes, this area of this cross-section. Notice that y is not changing. Very importantly, that's the point. It is for that specific fixed value of y that I'm trying to compute this cross-sectional area. I need y not to change. So this y in here, we're going to treat it like a constant because it is a constant. And if this smacks of partial derivatives, that's a good motivation for the way we refer to this integral here. We call this a partial integral. It's an integral of a function of two variables where I just treat one of them as a constant. Okay. Now notice that means that x is my only remaining variable. Does that make sense? Is x actually a variable? Well, yeah, look, you can see as I go across here, right, x is going from some starting value to some ending value, and there you go. X is going from A to B. X is my variable. Everybody on board? That's really not that weird. In context, this is just a single variable integral. Okay. Alrighty. So all together then, and let's zoom out so we can see what's going on here. All together then, if I want to compute, if I want to compute this volume, this total volume is an integral. It's an integral dy, as we argued a few minutes ago. Where my integrand is this cross-sectional area. That cross-sectional area, that integrand, that area itself is a whole separate integral. So you can see here what I actually have is an integral sitting inside of another integral. Which again, it's a little creepy, a little scary to look at, right? Integral inside of an integral, can you do that? And yeah, sure. No problem. Okay, so this is called an iterated integral. This whole thing together, the integral inside of the integral. Oh, let's see here. So this whole great big thing is an iterated integral. The dy integral of the dx integral of that original, whatever that original function was, f. Oh, sorry, purple. This f. Yeah. Everybody on board? Okay, so who cares? We just computed volume. Why are we interested in computing volume? What we're really interested in is computing masses and populations and work and all sorts of other applications. I want to know how to compute the answers to all of these questions, not just one particular little silly little geometry problem of volume under a surface. Right? So is that, how do I adapt? How do I deal with all these other problems? And the answer is I kind of do a little quick hand wave, and that is to notice that, well, previously we computed these volumes as double integrals. I just got through computing that same volume with an iterated integral. And now, again, I set rigor aside. My apologies. If you're interested in seeing something more rigorous, this isn't the right class for that. But I mean, if this is equal to that and that's equal to the other, then this is equal to the other, right? And so think of this iterated integral not so much as a tool for computing volume. Give me 2 seconds. Not so much as a tool for computing volume. Think of it as a tool for computing double integrals. Yeah. Yes.
So does it not matter at all which variable you do first?
That's a great question. It turns out that it does not make any difference in this case. That's right. It does make a difference sometimes, and we're going to explore that pretty thoroughly. But that's a long conversation. Yeah. But certainly from a geometric point of view, your volume is sum of, look, if you take a loaf of bread, you could slice it that way or you could slice it that way, right? Volume's still volume. And that's certain, if that was the intention of your question, the absolute yes. Yeah. Right. And the detailed devils will be different. Okay. Alrighty. So here it is then is an example how to do this. Suppose I want to compute the mass of a sheet of metal that sits over a rectangle in the XY plane. Let me draw that picture in the XY plane. Let's see, my rectangle has X going from 1 to 3, and then it has Y going from 2 to 4. Right, so my rectangle, my total overall rectangle is sitting there like this. So I want to compute the mass of that thing, where, X ranges as indicated, Y ranges as indicated. Mass is distributed like this. So, there's different densities at different locations. The further you are away, the more dense it is. Right? And the closer you are, the less dense it is. Right? So how do you compute the total mass of this thing? Okay, well, it turns out that double integrals are the perfect tool. First observation I'm going to make is that old news, we already know this, is that mass is an accumulating quantity. Mass is double integral. Again, we talked about that on Friday. Take this area, chop it up into little pieces. On each little piece, density times area. No problem. Add it all up, double integral. Okay. We just argued that double integrals are computed with iterated integrals. Yeah. So that means I've got an iterated integral to compute, and don't forget, these iterated integrals were literally single variable integrals, right? This was this argument here that I can compute an x integral of whatever that expression is with just a single variable calculus argument. And this integral in here, I was just taking a y integral of this function from a single variable point of view. And so this is just a straight up compute at this point. And here's the details. Let's look at the inside integral first. Let's see here. Now you got to be careful, a little bit careful. Don't forget, for the purposes of the inside integral, the outside variable is to be treated as a constant. We need it to be constant. The whole point of that inside integral is that we're computing a kind of a, I'm going to say cross-sectional area. That was the geometric argument that we gave. Okay, so we're going to treat x as a constant, and this gives me the first landmine opportunity that I want to point out. You're going to see that x squared there, and you're going to have this urge, this compulsion to write 1/3 x cubed. Right? But don't. X is a constant here. Y is your variable. X is a constant. Right? And the antiderivative of a constant is constant times the variable. Again, don't forget your variable is y. So the antiderivative of constant with respect to y is constant times y. X squared y. Everybody happy so far? Okay. What about y squared when y is the variable? Well, then yeah, sure, 1/3 y cubed. Yeah, of course. Everybody on board? Heads up. You got to be careful with that. That going forward, part of your job is to always be on the lookout, always sort of head on a swivel. Wait a minute, which of these variables is a variable and which of these variables is a constant? What's going on here? What role is being played by which variable? It's your job. Yeah. Okay. Okay, so then these values, 2 to 4, y then goes from 2 to 4. One of my little superstitions I'll share is I like to not just write 2 and 4 over here. I like to write y equals 2 and y equals 4. Because when you plug those in, notice even though x is a constant, right? X is not changing. Just psychologically, wouldn't it be a bummer if instead of plugging in 4 for that variable y, what if you accidentally plugged it in for x? Right? I mean, it's, you could see how you're in a hurry and you're doing a calculation, you're thinking about the next step, right? And you just space for a second. So this is one additional layer of security, a little psychological tool. I hope you'll do that. You don't have to, right? But I really think it's a good idea, and I want to encourage everybody to put that little reminder in there for yourself. Okay. All right, so you put these in. Fundamental theorem of calculus, just like always, capital F of B minus capital F of A, subtract it all out, and the value of that integral is that. Now you say, well, that's not a value. That's still got a variable in it, x. Don't forget, x is a constant for the purposes of that inside integral. So, as far as that inside integral is concerned, that's just a value. And we're done with that inside integral. Okay. All right. And then you think to yourself, okay, wait a minute, but now do I continue to treat this as a constant? No. Treating x as a constant was just for the purposes of computing that inner integral. Where that integral came from in the first place was that I was doing an x integral where x is ranging from some starting value to some ending value. So now we're back to treating x as a variable, and for the purposes then of this outside integral, you anti-differentiate it with the usual rules. Everybody on board with the details of that calculation? Any questions? Everybody happy? Okay. And, Calc 1. Boom. Answer. Okay. All right. So, now let me address a thought that students have sometimes. Students think to themselves, oh, well, look, I can compute with an iterated integral anyway. Oh, yeah, go ahead.
So I just come back to the previous slide, but
yep.
I'm confused on why it was 20 there.
Oh, did I do my arithmetic wrong? Oh, gosh. Let's see here. Well, okay, so, well, you know what? It's going to be arithmetic, so either I'm wrong or I'm right. Either way, it's just arithmetic.
Okay.
So let's talk about it after class. And if I'm wrong, I apologize.
Okay.
But it's I can't quite in my head, right? Okay, so, yeah, so a big important idea, though, so students will tend to look and think, oh, okay, cool, well, the iterated integral does it then. So phooey on double integrals. Why do I need double integrals in the first place? I mean, maybe this was just a red herring, bad idea. We just didn't need to we just needed to push forward and realize that we can just plain old single variable integral, and just, problem solved. And that's not true. So it's a very important idea, to see why that's not okay. And let's look at the very first step that we take here, right? I rewrite mass as a double integral. How can I rewrite mass as a double integral? I can do that because here we go. We're given, the premise of this question is that we have some sort of density given as a function of position. Right? I know mass per unit area in a given location. Right? That's mass per unit area. Mass per unit area is something you can multiply by area and get mass. And all of these objects are things that we understand. Right? Mass. Got it. I know what that is. Area. Yep. I understand that one as well. Right? Okay. What would happen if you just decided to, let's just phooey on this. Let's just bypass that. Let's just immediately write down mass equals iterated integral. And your argument is, okay, well look, so the idea is that, x is going from 1 to 3, and for each value of x, I'm going to want to compute this integral, at which point I say pause. What is that? And you get around to looking in the details and realize that we're taking mass per unit area and we're multiplying it times length. And I don't know what that is. Mass per unit area is supposed to be something you multiply by area. Mass per unit area times a length. I guess you could say it's mass per unit length, but is mass per unit length an accumulating quantity? How am I supposed to get an intuition for that? You lost me. That's not really a good argument. Now, if you really want to cram it and make it work, you could make it work, but it's a very unnatural argument to try to make. It's just not naturally meaningful. Okay, so that's why we need the idea of a double integral. This makes sense physically. This is what allows you to take application questions and rewrite them as expressions. You can turn real world problems into math problems with double integrals, specifically 2-index Riemann sums. Okay. So you cannot bypass this step. And so here's my little roadmap. We have a slightly different roadmap here than what we had in single variable calculus. Here we need double integrals so that applications can connect to them. Got to have it. You can't bypass it. But we also need iterated integrals because our fundamental theorem of calculus only works for single variable integrals, and iterated integrals are simply made out of single variable integrals. So that's nice. So we need the iterated integrals for calculations, but we need double integrals for applications. If you want your calculations to mean anything. Okay? So the fact that these are connected is huge. That's the bridge that makes it possible to get there from here. Okay. All right. So we're going to be doing a lot of double integral problems of various different sorts over the rest of this, next couple of weeks. And so they're all going to have roughly the same sort of roadmap strategy. I'm going to call these 3 different stages of the calculation: phase 1, phase 2, and phase 3. And they're all different. Right? Phase 1 arguments are, chop it up, add it up kind of arguments, accumulation arguments. Phase 2 arguments, well, those were easy. Right? In the applications we did here, it's just, you just look at the bounds and just see, whatever defines the rectangle, that defines the bounds on the iterated integral. That's no problem. And phase 3 is, pretty much plug and chug. But that it has its tricky parts. Phase 3 is where you got to keep track of which variable is a constant, which variable is actually the variable now, and keep track of who's doing what. Okay. All right. Let me hit the pause button again. Any questions? Everybody happy? Okay. All right. Side note, it's going to turn out that this is actually harder than it looks. Phase 2 arguments. Turning double integrals into iterated integrals has got its tricky bits. And that's the next thing that we're going to talk about. You'll notice that everything that we've done so far has been about rectangles, rectangular domains. And that's very limiting, right? Life's full of stuff that's not made out of rectangles. I might want to compute a population of a state other than Wyoming or Colorado, or a county other than somewhere in West Texas. Right? I might have a lake, and I want to compute the population of fish in the lake. The lake might not be a perfect rectangle, right? Probably not a perfect rectangle. That's the next thing we're going to consider. What do you do with non-rectangular domains? How does that change integrals? Okay, so here's such a picture. Now, you'll notice I've drawn just the domain. And again, maybe this is a lake, but I would still like to argue that whatever it is that I'm computing, fish population, volume of water, whatever, total amount of pollution throughout that lake, I can chop it up into little pieces. Total population of fish is the sum of the populations of fish in each one of these little sub boxes. Okay. All right. I'm not going to write down the formalities of with the definition of a double integral of a non-rectangular domain, but it's mostly a problem of notation, of how do you indicate that only add up over the boxes that are actually part of my lake. Right? And so it's really nothing to worry about. But conceptually, it's exactly what you think it is. You chop up the actual lake. You add up over the actual lake. Okay. All right. How do you compute these things? How do you turn this into an iterated integral? Well, I'm going to make another volume argument. Let's, again, pretend that we have a z-axis here. Notice I have pre-existing x-axis and y-axis. Right? So let's just add on a z-axis, and suppose that we're computing a volume. And just for sort of a visual aid, let me something like that. I don't know. All right, so I've got this volume now. I hope you can sort of visualize this amount of volume in here. And I would argue again that the total volume, look at the loaf of bread. Slice up the loaf of bread. The volume of the loaf of bread is the sum of the volumes of the slices of bread. And here's a slice of bread. Something like that. That slice of bread is still has a volume, which is just the cross-sectional area times the thickness. That cross-sectional area is still an integral of height times length. Everything goes through the exact same way. Hardly anything changes. In fact, you may be wondering, does anything change at all? Only one little microscopic detail changes. That's the really good news. The one little thing that changes is the bounds, the inner bounds. There's nothing else changes at all. And just notice, though, that for a given value of x, if you want to know, what are the bounds on my dy integral? Let's see here. So y, this dy integral there, y goes from that starting, the left side of the slice of bread to the right side of the slice of bread. There's a starting point. And there's an ending point. And those starting and ending points depend on x. Right? Just imagine as x moves to the right, if x increases, as that x changes, these points move. Right here, my picture's gotten messy. Let me just clean up my picture. We don't really need that anymore. If x moves, these points move, and correspondingly then the bounds move. Yeah? You're still chopping it up, adding it up. It's still volume is the sum of the slices of volume. Everything else is the same. So that's all we have to deal with. The only thing that changes is that inner bounds now become functions. Now again, it's a little freaky to think about bounds and an integral being functions. Can you do that? And let me remind you, again, it's kind of an illusion. These look like functions, but they're not really, right? So keep in mind, for the purposes of this inner integral here, we're treating x as being a constant. Right? It is for that constant value of x that I want to know what the volume of that slice is, or what have you. Right? We treat x as a constant because it is a constant. It is a constant for the purposes of that inside integral. It looks like a function. We're going to treat it like a constant. Yeah. Cool. Okay. Likewise, if you're slicing it up the other way, again, you can slice bread however you like, right? But if you do your y slicing first, right? Then for a given value of y, depending on that value of y, you're going to have different starting and ending values of x that are going to vary. They're going to change. Right? Those upper and lower bounds are going to change as y changes. Okay. So x becomes a function of y instead of y being a function of x. Okay. All right. Real quick, a little bit of terminology. It's tempting to refer to the differentials as first and second, and sometimes you can even do that, depending on the situation. It might be unambiguous, but I'll point out that when you're doing the slicing process, the one that's on the outside represents the first slice that you're taking, right? But when you're doing the integral, when you're actually cranking it out, you do the inside integral first, computationally. Right? So it's just a little bit awkward. So I don't want to say you can't say first and second, but again, there is that ambiguity, and you got to watch out for ambiguity. I very often like to refer to, well, look, whichever one's on the outside, let's just call that the outside variable. And it's unambiguous. Clearly, outside means first as part of the slicing process, last as part of the computational process. So outside, inside. Anyway, it's just terminology. Everybody good? And so we proceed to examples. Okay, so what if I've got a domain here like this? My domain D is bounded by a couple of curves. Y equals x squared is that curve, and then y equals x plus 2 is that curve. Right? Suppose I want to do a double integral over this domain. Real quick, terminology. This word, D is bounded by, you're going to have to do some interpretations, appropriate interpretations of what is being asked. And it goes as far. So this bounded by means two things. On the one hand, it means that domain D is bounded. It means that domain D is not infinitely large. It does not extend to infinity in any direction. The other thing it means is that those curves make up the boundary of my region. Right? And so that dictates that it's got to be that region. If you're sloppy, though, you might misinterpret and think, well, hey, look, there's this region over here. This, extending infinitely in those directions. That region, its boundary is those two curves. But it's not bounded. Right? So, in some sense, the first part of these problems is to make a clear, confident interpretation of what is the domain that actually is bounded, and specifically is bounded by those exact curves. And in this case, it's this one. So, there's kind of a geometry problem implicit in the wording of these questions. Okay. All right. So there we go. There's a question of which way to slice. Should you do dy dx or should you do dx dy? And there's some considerations there. One of the considerations is to avoid slicing through corners. Exactly why and what does that look like is something that we're going to talk about soon. So for the moment, let me just kind of bypass that question, but we will come back to that. So what we're going to do for this problem is we're going to do our first slices to be x slices. So, said differently, I'm going to put my dx on the outside. Right, and you'll see that in the integral that I have down at the end. X is on the outside. Okay. All right. Right. So, here's what x slices look like. And by the way, another little bit of terminology. I call those x slices because they are perpendicular to the x axis. They represent constant values of the x variable. Some students seem attached to the idea, but they're parallel to the y axis. That's not the point, right? Algebraically, these are connected to x. So we're going to call these x slices. Is everybody on board? So again, it's very important that we all speak the same language. So x slices will refer to slices as part of the process of moving along the x-axis. Okay. Yeah, so we start there, we end here. What are the bounds? There's a process for figuring out what the bounds are. It's very methodical, but you got to be careful. Don't look at the question and just think, the bounds are what feels right. You just kind of take what's written and, it's got to you sort of stick it in there and that's got to be right. Right? Not so. By the way, nasty trick. Some of y'all have had high school courses in multivariable calculus. In those high school courses in multivariable calculus, very often they give you a much more restricted category of domains And in this very restricted category of domains, it may actually be true that there's some sort of, directly from the phrasing of the question, you can just write down what the bounds are. That's not going to work in this class at all, for two reasons. One of them is our domains are not going to be that restricted. We're going to be considering much more general domain. It's just not going to work. The other thing is, don't forget, this is a class about ideas, not a class about answers. Right? If you don't justify your ideas, then you're not giving me what the points are being awarded for. Right? And, well, I just thought that's what you do is not an idea. Everybody on board? I want to be clear. I want to be emphatic. Okay. All right, so how do you find these bounds? Here's the idea. We've already agreed that the bounds that we're looking for, let's start with the lower bound, are determined by certain points that we can see in the picture, right? That's the first, that point represents the first slice that we do in that slicing process. Oh man, I missed it. Okay, so the bound is going to be determined by some point. Clearly and confidently identify what is the point. Next, notice that point is on certain curves, right? That point there is on that curve. And it's on that curve. Okay, so the bound is determined by certain points. The point is on certain curves. Next observation, those curves are on certain, those curves have certain equations. Whoops, sorry, wrong color. This curve has that equation. This curve has that equation. Okay, so now we're connecting a lot of dots here. The bounds are determined by a certain point. The point is on certain curves. The curves have certain equations. And now we've got some algebra. And this bound that we're looking for, that is something that you're going to get by taking these equations that you've worked your way into and solving for the variable that you're interested in, right? We're looking for a bound on x. We're looking for an x bound, and so you need to solve for x in these equations. That's actually not hard in this case. If you want to solve for x, you just notice that the y there can plug into the equation that has the y over here, and you get x squared equals x plus 2. Solve for x, and there's that -1. Everybody on board? Everybody see the process? It's always the same process. Bounds are determined by points. Points are on certain curves. Curves have certain equations. Make sure you solve for the variable that you actually need. Don't solve for y. Right? We're looking for a value, a bound on the x integral. So solve for x, and you're good. Okay, likewise for the upper bound, this upper bound is determined by that point. That point's on the exact same two curves with the exact same two equations. You therefore do the exact same algebra. You're just going to pick the two in this case. Okay. Everybody happy? Okay. All right, it's all details from here on out. So let's look at the inner bounds. I guess it's a little different for the inner bounds, but there's really not much. Those inner bounds. So we're looking now for a particular value of x. We're going to pick an x somewhere between -1 and 2, arbitrary, unknown x. For that value of x, I want to know my inner bounds. My bounds are determined by these points. Those points are on certain curves. Those curves have certain equations. And it is different between the two of them. For the lower bound, it's on that curve. By the way, thank you, picture. The picture tells us that, right? If you're just looking at the statement of the algebra here, you got a couple of equations given to you. How do you know which one's the lower bound, which one's the upper bound? The picture tells you. You can see it right here in the picture. That lower bound is on that curve that has that equation. And we solve for what we want. Again, we're looking to find a y bound. So in this equation, I need to solve for y. Good news, it's already solved for. Sometimes you get lucky, right? And that's your lower bound. Everybody happy? Lower bound is determined by a point. Point's on a curve. Curve has an equation. Solve for what you need. Again, solving for y because we're looking for a bound on a y integral. Okay. The upper bound. The upper bound for y. Well, it's determined by that point. That point is on that curve, which has that equation. Looking for a y bound. So we solve for y in this equation, and I get that. Same process. Okay. And now you've got a double integral, and off you go. Compute. Yep.
Why don't we choose outside as y?
Yeah, no, that's a great question. So this is something that I'm gonna talk about in the next few pages. Yeah, it can be a hard decision. In this case, I wanted to kind of bypass that just to get the mechanics of the process going. Yeah, right. Okay. So computationally, how does this change things? And the answer is very little, hardly at all. So again, suppose you want to compute a mass. Well, we already wrote down that masses are computed with double integrals. Double integrals are iterated integrals. For this particular domain, we just got through working out that domain, if you do your slicing in that order, has these bounds. That's the example we just did on the previous page. So for that shape domain, doing a double integral of that density, right? And now we've plug and chug. Now, again, be careful. Make sure to remember what variable is playing what role. For the inside integral here, y is your variable. Notice that y integrates like a variable because it is a variable, right? And remember, though, that the outside variable, it's a constant. We treat it like a constant because it is a constant, right? Again, for that inside integral, x really is fixed as I go from there to there. Okay. Right. Okay. So the only difference is that when you plug in, right, so these bounds, y goes from x squared to x plus 2, it just means that you're sticking in variables instead of sticking in constants. And it's just algebra. And so it remains that you'll have some great big expression here that you will have to do an x integral of. It's just you just have another source of algebra. No big deal. Everybody on board? Okay. All right. Let's see. I guess this may be our last example here because, oh my gosh, wow, time flies. Okay, so suppose you want to compute the volume under the graph of that function between these three curves, and notice y equals 0, y equals x, x equals 1. Those three curves define this region, so that's our domain. Volumes are double integrals. Double integrals are computed with iterated integrals. I'm skipping right to the ensuing iterated integral. If you were to do your x slicing first, x goes from 0 to 1. The picture pretty much tells us, right? You can play the game if you like, but it's clear. And then for a given value of x, once you fix x, right, looking at the y bounds, y is going to go from there to there. Think about these points. What do you know about those points? They're on which curves? Curves have what equations, et cetera, et cetera. And those bounds give you these bounds on the y integral. Okay, if you were to do it the other way, same domain, same exact domain. Just instead of doing your x slicing first, if you were to do instead your y slicing first. So switching the order of the differentials. What I want you to notice about the result here is that it's no longer the case that you can just kind of switcheroo the bounds also. For rectangles, that works. It's kind of a coincidence that works for Ray. It's because rectangles are really nice shapes that you can do that. But notice it's just not true here. Here, y goes from 0 to 1 if you're doing your y slices first. Right? And that's just not what I had for my y bounds up there. Likewise for the x bounds. So heads up, don't play it too fast and loose with switching the order of the differentials. You do have to go through the whole slicing process again. Okay, that's a good place to stop it for today. And we'll pick up here on Wednesday. See y'all later.